Alright, well this lesson is all about determining whether two polygons are similar. If two polygons are similar, two things are going to have to be true. Corresponding angles are going to be congruent, and corresponding sides are going to be proportional. Now let me make it clear. Well, first of all, this is a parallelogram. We can tell because of the way the opposite sides are congruent. Alright, for both shapes, opposite sides are congruent, it's a parallelogram. So that helps us know that, hold on a second. So this is 120 degrees, then this is going to be 120 degrees. Alright, similarly, these angles are going to be supplementary. So this is going to be 60 degrees, and this is going to be 60 degrees. Now the same thing is happening over here. So I've got 120 degrees, this will be 120 degrees, this will be 60 degrees, and this will be 60 degrees. So, excuse me, you can see that the angles are all going to be the same. Corresponding angles are congruent. Now, the thing that we have to check next is we have to make sure that the corresponding sides are proportional. So here's what we mean by that. If we make some ratios, okay, so for example, corresponding sides, clearly these would be corresponding sides, right? The 5 and the 1.5. It's a short and another short. Now, if I make a ratio out of that, so for example, let's say if I make a fraction 5 over 1.5. Let's see what we get. Okay, that gives us 3.3 repeating, which is the same thing as 10 over 3 if we toggle it. So this is equal to 10 over 3. Now let's look at another pair of corresponding sides. Alright, let's look at along and along. So let's do 18 over 5.4. Alright, now if these are proportional, we should get the same fraction every time we make a fraction out of corresponding sides. So let's see if we get the same thing. So let's go 18 over, and what was it, 5.4, I believe? Okay, there's our 3.3 repeating again, and of course if we toggle it, that's 10/3 once again. So that's what it means when we talk about corresponding sides being proportional. If you make a ratio out of corresponding sides, it should always make the same fraction. So if that happens, then that means the figures are similar. Alright, to be clear, that's two things. If the angles are the same, if corresponding angles are congruent and corresponding sides are proportional, meaning same ratio. Okay, let's take a look at number 2. Okay, are these two triangles similar? If so, we need to explain why they are. Well, we are looking for two things. Are the corresponding angles congruent? And are the corresponding sides proportional? Let's start with the angles. We have a 90-degree angle and another 90-degree angle. Okay, so we have that. So far, so good. I'm trying to color coordinate a little bit. We have a 74-degree angle and another 74-degree angle. And we have a 16-degree angle and another, I should double mark that one, and another 16-degree angle. So we do have all three angles congruent. So far, so good. Now we need to check to see if corresponding sides are proportional. Okay, so let's pick a pair. Now, clearly the hypotenuses would be corresponding, all right, if these are indeed going to be similar. So let's start with this. So let's go 100 over 25 and see what we get. Well, this we can do in our heads, all right. 25 goes into 100 4 times. So if these are similar, we should get 4 every time we make a ratio of corresponding sides. Let's do the pink ones next. Okay, so across from the 74, we've got the 96. Across from this 74, we've got the 24. So these two should be corresponding sides. So let's go 96 over 24 and see if we get 4. Oh, look at that. It's looking good so far. All right, those pairs of corresponding sides are proportional, but we will not have it for sure until we check the third angle. All right, the third sides. So we have the 28 and the 7. So we have 28 over 7. And yeah, of course, 28 divided by 7 is 4. Okay, so by the definition of similarity, these two triangles are similar. Okay, so I'm just going to list off the two parts of the definition. We can say yes, these two triangles are congruent because number 1, corresponding angles are congruent, and number 2, corresponding sides are proportional. Now, just in case, let me be thorough and say that in a future lesson, we're going to learn shortcuts and postulates and theorems that will allow us to decide that two triangles are similar without knowing that all 3 angles are congruent and all 3 sides are proportional. But for now, let's stick to the definition. We'll save the shortcuts for a future lesson. Okay, number 3. In this diagram, triangle ABC is similar to triangle EDC. Alright, so ABC is the big triangle and EDC is the smaller triangle. So it's like this. So write the statement of proportionality. Alright, the statement of proportionality is an equation where all of the corresponding sides are put into fractions and set equal to each other. For example, AB and DE are corresponding sides. So they should be proportional. And let's see, how about the bottoms? AC, all right, is the big bottom, and EC is the small bottom. They should be proportional to each other. All right, how about the hypotenuses? Let's do the big hypotenuse first. So that's BC. All right, and BC should be proportional to DC. So this is a statement of proportionality. Okay, if two polygons are similar, then corresponding angles must be, drumroll please, congruent. All right, they've got to be exactly the same. They've got to be congruent, not supplementary, not complementary. Linear pairs doesn't make sense. I guess that would be like supplementary in a way. But congruent is the answer. Yeah, let's roll straight into number 5. If two polygons are similar, then corresponding sides must be proportional. That's what we've been saying this whole time. Okay, yeah, that's not much else to it than that. Let's move on. Alright, which triangle is not similar to any of the others? Well, let's start with the angles. Alright, 45 degrees, 45 degrees. They have to add up to 180, so you know the other one's going to be 90. Okay, 45, 45, 90, that adds up to 180. Here I've got 45 and 90. The other one's got to be 45. That's the only way it adds up to 180 degrees. So far we've got a 45, 45, 90, another 45, 45, 90. Okay, all three angles are congruent. Now, this one I have the 90. Do I have any idea what these are? Sure I do. Alright, these two have to add up to 90. But yet, because of these markings, I see this as isosceles. And the base angles of an isosceles triangle have to be equal. So if I take my 90 degrees and divide it by 2, this has to be 45 degrees and 45 degrees, just like the previous two. So if these are going to be similar, the corresponding angles have to be congruent. So these three triangles certainly appear to be similar based on the angles being congruent, all right? Three pairs of congruent angles. A does not fit this pattern. This is an equilateral triangle. That means all three sides are the same, which means all three of these angles are going to be the same as well. Mess that up a little bit. I said boy, I say boy. All three of these angles are going to be the same. So if I take 180 divided by 3, that is 60, 60, and 60. So these angles do not match. They are not congruent. So it is A that is not similar to any of the others. Okay, what about number 7? Alright, triangle ABC is similar to, that's what that symbol means, triangle DEF. And triangle DEF is similar to triangle GHI. If that's the case, then what's true? Well, I'm not sure if this is where they're headed, but it certainly would be true that triangle ABC will be similar to triangle GHI. Okay? Like bridge that gap. All of these triangles are similar. Is that one of the choices? Triangle ABC is similar to triangle GHI? Well, yeah, so that's the obvious answer, number 7. Okay, fantastic. Number 8. Whoa, too far. You've gone too far this time, sir. Alright, let me zoom out a bit. Alright, number 8. A photo needs to be enlarged from an original with a length of 11 inches and a width of 9 inches to a size where the new width is 45 inches. What is the new length? What is the scale factor? Let's go to the black screen. Alright, so let's say this yellow is the original and this pink is the new picture. Alright, according to the story, the original photo was 9 by 11. Okay, so let's get that in there. So this was 9 by 11. But it needs to be enlarged. Okay, to a size where the new width is going to be 45 inches. Okay, so my new width, instead of being 9, is going to become 45 inches. Now, so we're enlarging, so it's got to be proportional, alright? Which means the corresponding sides have to make the same ratio. Another way to look at it is to look at it as a scale factor. Okay, this one's easy because it's a straight multiple. So my scale factor, what am I multiplying by as I turn 9 into 45? Alright, obviously 9 times 5 is 45, so that's going to be my scale factor. Alright, is that multiplier. So the thing is, it's got to be the same scale factor all the way around. So when I go from a height of 11, I also must be multiplying by 5. So that means it must be a new height. Maybe I'll just stick with this. It must be a new height of 11 times 5, which of course is 55. So the new height must be 55 inches, and the scale factor is 5. Okay, so what is the new length, I guess they call it instead of height? The new length is 55 inches. And the scale factor was 5. Okay, moving on. Number 9. One standard photograph size is 4 inches by 5 inches, a 4 by 5 rectangle. Which of these other rectangular sizes is similar to it? Okay, so 4 by 5. So what you want to do is go ahead and put this in terms of a ratio. And so we will simply look for the one that makes the same ratio. So if we go 4 to 5, all right, let's go ahead and put that as a ratio. Let me zoom in. Okay, so we've got this 4 by 5 situation, but if I go 4 to 5, okay, it might be useful to go ahead and know the decimal of this. So 4/5, obviously as a fraction does not reduce, so that's just 4/5. But as a decimal, we're talking about 0.8. So as soon as we see 0.8, we know we've got a winner. Okay, so remember we're going small to big, small over big. So let's just do the same thing here. If I go 5 to 7, all right, it's 5 over 7. Well, you know, we don't need the decimal to know that that does not reduce to 4/5. Okay, but if we put it into a calculator, just another way of looking at it, 5 to 7, okay, decimalize it, that's 0.7, blah, blah, blah. It's not 0.8, so A is not the answer. Okay, for B, 8 to 10, all right, if we look at that one, 8 to 10. Okay, well we would reduce that, right? Both of these are divisible by 2. Guess what? That reduces down to 4/5. Okay, we have a winner. So that's why the answer is going to be B. All right, it's just really not that much to it. Let me be clear though. I mean, B turned out to be the answer, but how would you deal with mixed numbers like this? Well, I think an easy thing to do would be to turn both of these into improper fractions. Okay, 2.5. Okay, please understand that 2.5 is like 2 plus 1/2. Okay, that's 5 halves. Do you understand me? Okay, so let me change colors. So this is the same thing as 5 halves. Similarly, 3.5. Okay, 3.5 is like 3 plus 1/2. Alright, that's 7 halves. Okay, so if I made a ratio out of these, that ratio would be 5 halves divided by 7 halves. Okay, that's what we were doing with the other ones by doing 8 divided by 10. Alright, it's the same thing. 5 halves over 7 halves. But maybe you know that when you divide by a fraction, it's the same thing as multiplying by the reciprocal. So this would be the same thing as 5 halves times 2/7. Okay, and maybe you'll notice that these 2's will cancel each other out, and you're going to wind up with 5/7. Otherwise, if you didn't notice that, then you would have to go, oh, well, this would be 10 over 14. All right, just multiplying straight across. And then that reduces down. They're both divisible by 2, so that's 5/7. And then you would look and go, oh, look, 5/7. That is not the same thing as 4/5. So I just wanted to show you what to do if you have mixed numbers. Anyway, let's move on to number 10. Which image does not show a dilation? Okay, what are we looking at here? Okay, well, so in this A, we're talking about this inner quadrilateral and the outer quadrilateral. Well, if it's going to be a dilation, then the smaller shape and the bigger shape should be similar. Okay, so this is clearly a dilation because we have a square and then a bigger square. Those are going to be similar. So, all right, that's definitely a dilation. Okay. Okay, I'm going to come back to B for a second. Looking at C, you can tell by the way that, see how these lines are drawn vanishing to a single point? That's going to make it so that these shapes are in fact going to be similar. This is like a projection. Okay, you can see that the lines are traveling and expanding, so you're guaranteed to be similar. So when you have this type of situation where the lines are all converging on a single point, then yeah, these shapes are definitely going to be similar. Same thing is happening here with D. See how all of the lines again are converging on a single point. Okay, that means that this is definitely going to be a dilation with a center, this point as the center. You know, notice that these distances are proportional. Maybe we're doubling or something. But anyway, these are definitely going to be similar because of the way that the lines are converging at a single point. That is not what's happening. B is the one picture where we do not have all of these lines converging at a single point. This is not necessarily a dilation. So the answer is B. Now let's ignore their little lines for a minute. Let's draw our own lines and see if they converge at a single point, because that's what they should have drawn if these were supposed to be if this was supposed to be a dilation. So let's draw our own lines and see if they converge at a single point. Alright, there's one line. Alright, here's another line connecting corresponding vertices. Now as I put in this third line, you see that it's not meeting where the other two met. Okay, it's missing that intersection point. So right away that shows that these are not similar, alright, because of the way the intersecting lines, if you draw lines sort of connecting the vertices, they are not converging at a single point the way it does when you have a dilation. Okay, but let's go ahead and draw the fourth line just to finish it up. Okay, and there's the fourth line. Again, there's no way that these four lines are converging and meeting at a single point. If they did, you know, the way that we see in the other three images, see the way these lines connecting vertices all meet at a single point, that would be a way of showing that you're looking at a dilation. Alright, number 11 is the last one. The dashed triangle is the image of the solid triangle formed by a dilation centered at the origin. Find the scale factor of the dilation. Okay, so again, the solid triangle is the pre-image and the dashed triangle is the image. Alright, in other words, we're looking at a transformation where the solid triangle becomes bigger. Alright, so that means the scale factor is going to be something bigger than 1. Now, to figure out exactly what it is, I think it would be helpful to know what the coordinates of some of the vertices are. Alright, all we really need is a one pair, really. Let's see, what do we want to do? Let's look at this pair right here. Let's look at these vertices. Alright, these are corresponding vertices. Now, this one in here is nice and easy. It is 1, 1. Okay, now the image of this point, alright, is, what do we have? 1, 2, 3, 1, 2, 3. So this is 3, 3. I really messed that 3 up. I had a little lag there. I'm going to blame it on the computer lag. It's not my fault. So you can see what the scale factor must have been. Alright, if 1, 1 is going to become 3, 3, we must be multiplying by 3. Alright, so the scale factor must be 3. Okay, just for the sake of thoroughness, let me be clear that another way to calculate the scale factor is by taking a number from the image. Okay, if you do the image, in other words, like the final picture, and you divide by the pre-image, okay, which is the original. That should give you the scale factor as well. Okay, so in this case, the image, like for example, if you look at the x value, you only need 1, but the image is 3, the pre-image was 1, and 3 divided by 1 is 3. That's another way of looking at how we get the scale factor. Alright, and that is it for this lesson. I hope this was helpful for you, and I will see you on the next video.